In this video, I'm going to give a brief explanation and recap of our opening day ball drop activity. In this activity, if you recall, a ball was placed immediately below a sensor. The ball was then dropped, and its subsequent position relative to the sensor was measured at 0.05 second increments. We did this several times, and in the spreadsheet before you lies one of the drops that we did in class, the second one, I believe. So if you look at this data, the first column is a series of time measurements, which all differ by 0.05 seconds. The second is a sequence of position measurements, where position is measured in meters. So if we wanted to add to this table right here a column for average velocity at various times during the drop, then we could do this. And since velocity is a rate of change of position, or in other words, the change in position over the change in time, we can calculate the average velocity by subtracting successive positions and dividing that by the changes, the corresponding change in time. So for example, over this first 0.05 seconds of the drop, to compute the average velocity, we would enter B3, the cell containing the velocity at the end of that interval, subtract from that B2, the velocity at the beginning, and divide by 0.05, which is the change in time. So over this first brief interval here, the ball was traveling with an average velocity of 0.4 meters per second. Now, the nice thing about Excel is once we've done this for one cell, because of relative referencing, we can simply move our cursor until it changes to a dark cross in the right corner and drag this down, and Excel will compute the average velocity for every other time interval for us. Now, in the activity, we went beyond velocity, which you recall velocity as a division is measured in meters per second in this example. But we went beyond this to actually also estimating an acceleration for the ball drop. Right? Now, acceleration is a change in velocity. It's a rate of change of velocity. So to compute acceleration from velocity is analogous to the computation we just performed between velocity from position. So for example, if I wanted to compute the average acceleration at over this first this 0.5 interval right here, then what I would have to do is I would have to subtract the velocity measurements. But let me do it as cell references so that we can maintain our relative referencing structure here, and divide that by, again, the change in time. So over this first interval right here, the ball accelerated at a rate of 24, and the units for that would be meters per second squared, because we're taking velocity and dividing it by time. And once again, I can drag this formula down to these other cells and compute the average acceleration of the ball over each successive interval here. So one thing now is we can see that the acceleration was not constant, at least by our data's measurements. However, Galileo did discover 500 years ago that gravitational acceleration, which is the primary force acting upon the ball in this experiment, should provide constant acceleration. So gravity as a force should provide constant acceleration. And so any differences between that are actually, in this case, due to data error. So to get a better idea of what that constant acceleration could be, we could average these data points and see what the average acceleration is for the ball over all of its intervals of travel. Now, in doing that, though, we might also want to make note of the fact that the first measurement and the last measurement were much larger than the other ones, and we might want to exclude those because it's possible, especially at the beginning, at the end, that there was just too much noise in the data, right? I mean, at the beginning, it's maybe moving the ball too much, or maybe released it at an angle or something like that. And then also at the bottom, it's actually possible that the ball hit the ground in between these two times and started coming back up, in which case this last measurement would be incorrect. So what we're going to do is we're just going to average these cells right here. So what I'm going to do is I'm going to type average, highlight the cells I want to average, hit enter. And notice we come up with an estimate for gravitational acceleration of 9.6 meters per second squared, which is actually fairly close to the true value of 9.81, or approximately 9.81 meters per second squared. And all this from a first day calculus experiment.